Spring 1993, an Intel engineering lab. A brand new processor, the most important chip the company has built in years, sits on a test bench inside a running system. The engineers watching it aren't checking its speed. They're watching its temperature. The chip is running hot enough that only half-jokingly, someone in the lab has taken to resting a coffee mug near it between tests, because the thing genuinely puts out enough heat to keep a drink warm. Nobody is laughing for long. This chip is supposed to be the future of Intel's entire business, the processor meant to define personal computing for the next several years. And right now, it runs so hot that some of the very engineers testing it privately wonder whether it's actually safe to leave running inside a closed computer case without something actively blowing air across it. That chip was the original Intel Pentium, and the nickname that stuck to it inside engineering circles, the coffee warmer, wasn't really an exaggeration. For over a decade before this moment, a computer's main processor had been something you never needed to think about thermally. It sat on the motherboard, drew a trickle of power, and ran barely warmer than the room around it. Nobody built cooling systems for it because nobody needed to. The Pentium broke that assumption completely, and in doing so, forced an entire industry to permanently change the way it built computers, creating, almost by necessity, a piece of hardware that has been sitting inside nearly every computer built since: the CPU fan. This is the story of how Intel's most important chip of the early 1990s nearly became a public embarrassment because of a problem nobody in the industry had ever seriously had to solve before, and how the fix for it became one of the most permanent, unglamorous fixtures of modern computing. To understand just how strange a problem this was for Intel to be facing in 1993, you first have to understand what normal looked like for a computer processor for the entire decade before it. A world where heat simply wasn't part of the conversation at all. To understand how strange this problem was in 1993, you have to understand just how little anyone in the PC industry had ever worried about processor temperature before. Intel's early chips, the 8086, the 80286, even the original 80386, ran at clock speeds measured in single-digit or low double-digit megahertz, drew only a few watts of power, and sat on the motherboard as bare, unadorned pieces of silicon. You could touch one while it was running and feel, at most, a faint warmth. Heatsinks, when they appeared at all, were an afterthought reserved for unusually demanding setups, not something the average PC builder ever needed to think about. Even the 80486, Intel's workhorse processor, through much of the early 1990s, mostly got by without dedicated cooling. Early 486 chips ran comfortably with nothing more than the ambient airflow already moving through a computer case, kicked up by the power supply's own exhaust fan. It wasn't until the faster 486 variants, chips like the 486DX266, which doubled its internal clock speed relative to the bus feeding it, that manufacturers started recommending an actual heatsink for the first time. Even then, a heatsink alone, a simple finned block of metal sitting passively on top of the chip, was usually enough. Nobody yet needed a dedicated fan bolted directly onto the processor. That idea would have struck most engineers in 1991 as slightly absurd, over-engineering for a problem that didn't really exist. There's a reason this blind spot lasted as long as it did. Engineers designing PC cases, power supplies, and motherboards throughout the 1980s built their entire mental model of heat inside a computer around a small number of known offenders: the power supply itself, which converted household electricity into the voltages a computer needed, and inevitably wasted some of that energy as heat in the process, and in higher-end machines, hard drives with spinning platters and motors. The processor sat quietly in that model as a minor, almost incidental source of warmth, not worth engineering around. Case designs reflected that assumption. A typical desktop tower from the late 1980s or very early 1990s might have a single fan built into the power supply, expected to handle the thermal needs of the entire machine. Nobody drew airflow diagrams pointing air specifically at the processor because nobody needed to. Which is exactly why what happened next caught so much of the industry off guard. By the start of the 1990s, Intel faced a branding problem as much as an engineering one. The company's processors had up to that point been named with simple numbers: the 286, the 386, the 486, a naming convention that made sense until competitors like AMD started producing their own compatible chips and marketing them under the same numeric scheme. Intel discovered, to its frustration, that it couldn't trademark a number. A string of digits was fair game for anyone to use, which meant Intel's next major chip needed something a rival couldn't simply copy onto its own competing product. The solution was a brand name instead of a number: Pentium, derived from the Greek word for 5, marking this as Intel's 5th-generation x86 architecture, but now protected in a way 586 never could have been. The stakes riding on that name were real. AMD and Cyrix were both building increasingly capable 486-class chips, chipping away at Intel's margins and its reputation as the only serious choice for a PC's brain. Intel couldn't afford a lukewarm follow-up act. The Pentium needed to be unambiguously, dramatically faster and more capable than anything a competitor could put on a shelf next to it, and it needed to arrive on a timeline that kept Intel ahead rather than playing catch-up. That competitive pressure shaped almost every engineering trade-off that went into the chip, including, as it turned out, the one that would cause the most trouble. But branding wasn't the only pressure riding on this chip. The Pentium needed to be a genuine technical leap, not just a renamed successor to the 486. Intel's engineers built it around a superscalar architecture, with dual integer pipelines allowing the chip to execute more than one instruction per clock cycle for the first time in a mainstream x86 design, along with an integrated floating-point unit and a wider 64-bit data bus. Packed with roughly 3.1 million transistors, more than double what the 486 carried, this was a fundamentally more complex, more powerful piece of silicon than anything Intel had shipped before. And all of that additional complexity needed somewhere to draw its power from, and somewhere for the resulting heat to go. Here's where the trouble actually started, and it came from a decision that at the time looked like the pragmatic choice rather than a reckless one. To hit its launch schedule, Intel built the first Pentium chips on a 0.8-micron manufacturing process. By 1993 standards, not the cutting edge, but mature and well understood, which mattered enormously for a company that needed to ship a complex new architecture reliably and on time. That manufacturing process, however, meant the chip had to run on a 5-volt power supply, the same voltage earlier, much simpler chips had used. 5 volts might have been perfectly reasonable for a chip, with a fraction of the Pentium's transistor count and complexity. For a chip carrying 3.1 million transistors, running dual pipelines, and clocked at speeds far beyond anything Intel had shipped before, 5 volts turned out to be a serious liability. Power consumption, and the heat that comes directly along with it, scales sharply with both voltage and transistor activity, and the Pentium was pushing both dramatically higher than any of its predecessors. The 60 MHz version of the chip alone could draw upward of 15 watts under full load, a modest number by today's standards, where high-performance processors routinely draw well over 100 watts, but an enormous jump for an industry that had spent a decade building processors nobody needed to actively cool at all. The 66 MHz version of the chip made the problem worse still. To keep that slightly faster chip electrically stable, Intel had to push its voltage even higher, up to 5.25 volts, a small-sounding adjustment that, given how heat output scales with voltage, meaningfully worsened an already uncomfortable thermal situation. Engineers testing early Pentium systems started running into a genuinely new kind of problem: processors that, without adequate airflow, ran hot enough to threaten their own stability and, in worst-case scenarios, hot enough to risk damaging the socket and surrounding components on the motherboard itself. Inside engineering circles, and soon in the wider enthusiast press, the chip picked up that half-joking, half-damning nickname, the coffee warmer. For the system builders and motherboard manufacturers on the receiving end of this new chip, the experience of discovering the problem was rarely dramatic in any single moment. It was more a slow, mounting unease. A test system that ran fine for 20 minutes would start throwing errors an hour in. A machine that booted perfectly on an open test bench, with plenty of room for heat to dissipate into open air, would behave erratically once sealed inside an ordinary consumer case with its more limited airflow. Reports would trickle back describing sockets that felt uncomfortably hot to the touch, plastic components near the processor showing early signs of warping under sustained heat, and systems that would simply lock up under heavy, sustained workloads, exactly the kind of demanding tasks a flagship new processor was supposed to be marketed as excelling at. For a chip Intel was counting on to prove its next decade of leadership, this was not a small cosmetic issue. It was a direct threat to the reputation of the product itself, arriving right as competitors were watching closely for any sign of a stumble. What made this genuinely difficult to solve wasn't just the heat itself. It was that almost nobody in the PC industry had ever had to solve this exact problem before, at this exact scale, on a mainstream consumer product. Server and workstation engineers had occasionally dealt with thermal challenges on more exotic, expensive hardware, but the assumption baked into practically every consumer PC design of the era was that the processor itself was one of the least thermally demanding components in the box. Power supplies needed fans. Some high-end graphics hardware, in later years, would need fans. The CPU had simply never been on that list. That assumption showed up everywhere in how PCs of the era were actually built. Case airflow was designed around keeping the power supply and the general internal environment reasonably cool, not around directing concentrated airflow at one specific chip on the motherboard. Motherboard designs left the processor socket with a modest amount of clearance, enough for a simple heatsink, but not necessarily engineered with a dedicated fan mount in mind. System builders, retailers, and even some of Intel's own OEM partners had to work out, largely from scratch and largely under time pressure, exactly how much cooling a Pentium system actually needed to run reliably in the real world, in a customer's home or office, not just on a controlled test bench in a lab. Early attempts leaned on the same solution that had worked for the hottest 486 chips, a larger, more substantial passive heatsink, with more surface area to shed heat into the surrounding air. For the 60 and 66 MHz Pentium, even a generously sized passive heatsink often wasn't enough on its own to keep the chip running safely and consistently, especially inside a typical closed desktop case with limited internal airflow. The chip needed something actively moving air across it, not just metal fins. Hopping ambient air currents would do the job. Some system builders, in the scramble to figure out a workable solution before the chip's reputation took a permanent hit, tried simply oversizing everything: bigger heatsinks, more fins, denser aluminum blocks bolted onto the processor with whatever mounting hardware could be adapted to fit. It helped, but only up to a point, and it came with its own trade-offs. A heavier heatsink put more mechanical stress on the socket and the motherboard itself, and without any air actively moving across all those extra fins, a bigger passive heatsink mostly just meant a bigger, still too warm chunk of metal. The industry needed to solve the actual physics of the problem, not just add more surface area and hope. The solution, once the industry accepted that passive cooling alone wasn't going to cut it for this chip, was straightforward in concept, if genuinely new in practice for a mainstream desktop CPU. Attach a small electric fan directly to the heatsink sitting on top of the processor, creating a dedicated, self-contained cooling assembly mounted right where the heat was actually being generated, rather than relying on general case airflow to happen to pass by. Instead of hopping the power supply's exhaust fan pulled enough warm air off the motherboard, you put a fan exactly where it mattered most, blowing directly onto, or through, a heatsink that was itself sitting directly on the chip. This wasn't a dramatic single invention so much as an idea the industry converged on quickly, almost out of necessity, once it became clear that Socket 4 Pentium systems genuinely needed it to run reliably. Some early solutions were fairly makeshift by later standards: a small fan zip-tied or clipped onto an existing heatsink, powered by whatever spare connector a system builder could find on the motherboard or power supply. But the underlying principle caught on fast, because the alternative, a flagship processor with a real-world reputation for instability, or worse, for damaging its own socket, was something neither Intel nor its partners could afford to let stand. Within a short span of time, motherboard makers and system builders began treating an active fan and heatsink combination, mounted directly on the CPU, as standard equipment for Pentium-based machines rather than an optional upgrade for enthusiasts pushing their hardware to its limits. It's worth pausing on how significant that shift actually was. For roughly a decade before this moment, the processor had been the one component in a PC nobody needed to actively cool. After this moment, active cooling directly on the CPU became simply assumed, an unquestioned part of what a functioning computer needed, in exactly the same category as needing a power supply or a keyboard. Intel, for its part, didn't just let motherboard partners quietly patch around the problem and move on. The company's next major revision of the Pentium architecture, known internally as the P54C core, addressed the root cause directly rather than simply managing its symptoms. Where the original 60 and 66 MHz Pentium ran on 5 volts, the P54C generation, chips clocked at 75, 90, and 100 MHz and beyond, dropped to a 3.3-volt design. That reduction in voltage translated directly into a meaningful reduction in power draw and heat output, even as clock speeds climbed higher than the original chips had managed. It was, in effect, Intel quietly admitting that the original 5-volt design had been a genuine miscalculation, one worth correcting properly in silicon rather than permanently papering over with bigger and bigger fans. Even with that improvement, though, the industry never went back to treating the processor as a component that didn't need active cooling. The lesson had already landed too firmly. As chips got faster and more complex, power and heat were only ever going to keep climbing, not level off. When Intel later released Pentium Overdrive upgrade chips, designed to let owners of older 486 systems drop in a Pentium-class processor without replacing their whole motherboard, some of those upgrade chips shipped with a fan built directly into their own heatsink assembly, wired to draw power straight from the chip's own socket rather than relying on a separate connection elsewhere in the case. The dedicated CPU cooler, fan and all, had gone from an emergency fix to a standard, expected component of the product itself. It's easy, looking back from a modern computer with a cooling system that might include multiple fans, heat pipes, or even liquid cooling loops, to see the addition of one small fan on a 1993 processor as a minor footnote. But the shift it represented was bigger than the size of the fix suggests. The Pentium's overheating problem forced the entire PC industry to accept something it had never had to seriously reckon with before. That the relentless progress Intel and its competitors were chasing, ever higher clock speeds, ever more transistors, ever greater performance, was not a problem that clever chip design alone could solve indefinitely. At some point, physics demanded somewhere for all that extra energy to go, and simply hopping ambient air currents would carry it away was no longer good enough. Every major leap in processor performance from that point forward has come bundled with a corresponding leap in thermal engineering. Later Pentium generations pushed clock speeds and power draw higher again, requiring larger heatsinks and more capable fans. The Pentium 4, later in the decade, and especially its later Prescott revision in the mid-2000s, ran hot enough that its cooling assembly became one of the most physically substantial parts of an entire desktop system, with Intel and its partners racing to design heatsinks with ever more surface area and fans capable of moving ever more air without turning a home office into a wind tunnel. Graphics cards, once passively cooled or entirely fanless, eventually needed their own dedicated coolers as they took on more of a computer's processing workload, to the point where a modern high-end graphics card's cooling assembly can be larger and heavier than the entire graphics card that housed the first Pentium-era 3D accelerators. High-end gaming and workstation machines today often rely on liquid cooling loops, an idea that would have sounded like exotic laboratory equipment to a PC builder in 1992, but that traces its underlying justification directly back to the same basic problem the original Pentium exposed. A chip doing more work generates more heat, and eventually, air alone, however cleverly directed, isn't enough. There's also a whole enthusiast culture that owes its existence, indirectly, to this same moment. Once active cooling became a normal, expected part of a computer rather than an exotic add-on, it opened the door to overclocking, deliberately running a chip faster than its rated speed, and managing the resulting extra heat with increasingly serious cooling hardware. What started as an emergency fix for a chip that ran hotter than anyone expected eventually became the foundation of an entire hobbyist industry built around pushing chips harder than their manufacturers intended, using exactly the kind of dedicated, purpose-built cooling hardware that the original Pentium crisis had first made necessary. There's a small, almost invisible thread connecting a 1993 engineering lab worried about a chip warm enough to joke about heating coffee, and the quiet hum you hear right now if you're sitting near a running computer. That sound, the low, steady whir of a fan spinning somewhere inside the case, has become such a permanent, unremarkable feature of computing that most people never think about where it came from, or that there was ever a time when computers didn't need to make that sound at all. For the better part of a decade, a computer's processor ran silently, in the thermal sense as much as the literal one, drawing modest power and demanding nothing beyond whatever airflow happened to already be moving through the case. The original Pentium ended that quiet era for good, not through some deliberate strategic decision, but through the blunt, undeniable physics of trying to pack more computing power into a chip built on a manufacturing process that simply wasn't designed to handle it efficiently. The coffee warmer jokes stopped being funny fast enough that Intel and its partners had to solve the problem directly, and the solution they landed on, a small fan, mounted directly where the heat was actually being made, became so foundational to how computers are built that it has never really gone away since. It's worth remembering, too, that this wasn't a failure story in the way a cancelled product or a bankrupt company would be. The Pentium went on to become an enormous commercial success, the processor that genuinely did define an era of computing and cemented Intel's dominance for years afterward. The overheating problem never stopped it from succeeding. What it did was permanently rewrite one of the unwritten assumptions the entire industry had been building on for a decade, the assumption that a processor was something you never had to actively cool. Once that assumption broke, it broke for good, for every chip that came after it, on every desk, in every laptop bag, for the rest of computing history. Every time a modern laptop's fan spins up under load, every time a gaming PC's cooling system kicks into a higher gear, every heatsink and fan assembly sitting on top of a processor in a machine built today is a direct descendant of a problem that first became impossible to ignore inside a hot, humming test lab in the spring of 1993. The moment a chip Intel needed to be its next great success very nearly became famous for a completely different reason.